Graphs and points plotted on the Cartesian plane are a very good way of representing information. So we need to be able to be sure that we can read the stories told on the Cartesian plane. Let's have a look at an example. Imagine that I have a group of learners who've written a test. And I take that group of learners who've written a test and I plot on a graph the number of hours they spent studying for the test and also the mark they got out of 100 for the test. I use the x-coordinate to show the number of hours they spent studying and the y-coordinate to show the mark out of 100 for the test. So here's a plot of all my learners. You can see my learners have boring names, A, B, C, D, etc. Let's answer some questions about them. The first question, how many learners wrote the test? Well, as each point represents a learner, all we have to do is count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there were 11 learners who wrote the test. Who got the highest mark for the test? Well, remember, the marks are shown as the y-coordinate. So the marks, the highest mark will be the highest up. The y-coordinates are how far up you are. And so if you have a look, you can see that the highest up is learner K, and you can read off that learner K actually got 100 out of 100, full marks for the test. Who studied the longest for the test? Well, the number of hours spent studying is shown on the x as an x, the x-coordinate, and so the further you are to the right, the more hours you spent studying. So we can see that learner I is the learner who spent longest studying, and that learner spent 10 hours studying for the test. Who got the same mark as C for the test? Well, have a look at C. It's that little orange dot in the bottom left-hand corner. Well, you can see that C actually only got a mark of 10 for the test. And where else do we see a mark of 10, right? Can you see that it's anywhere along that orange line? That is where the mark out of 100 is 10. Who else lies on that line? Well, learner E also got 10 out of 100 for the test. Okay, what if we change the question to be who studied for the same amount of time as C? Well, C only studied for 1 hour. Let's have a look at who else would have studied for 1 hour. Can you see it's that orange line that has everybody who studies for an hour on it, right? That is where you have only 1 hour of studying. Who else lies on that line? It's learner D. Next question, name the learners who got 50% for the test, who got less than 50% for the test. Well, where is the 50% mark? It's there. Who got less than it will be the learners who are below that, and that'll be C, D, E, and F. And then finally, if there's another learner, L, who studied for less time than learner G but got a higher mark than learner B, where might you be able to put learner L on this? Where could learner L be? Well, let's have a look. Where's all the bits where you have somebody who's studying less time than learner G? Well, if you're studying less time than learner G, you have to be to the left of learner G. So in that green area. If you got a higher mark than learner B, you have to be above the mark for learner B. So you have to be in that red area. Now our learner L has to be in the green area as well as in the red area. So learner L could be somewhere there, or there, or there, or there, right? Anywhere in the overlap between those two areas. Let's have a look at plotting points to make a graph. You're very familiar with drawing up a table of values. Here we've got x being -4, -3, -2, -1, all the way up to 4. And we're going to work out the corresponding y values when y is calculated by saying x squared subtract 9. So when x is -4, how do we work out what the y value is? Well, we simply substitute -4 into that formula. We'll get -4 squared subtract 9. -4 squared is 16. 16 subtract 9 is 7. The thing that we're going to add on now is this. We've got an x value of -4, a y value of 7. We can write that as an ordered pair, and we can plot it on the graph. We plot it on the graph. X is -4, so 4 steps to the left, and then y is 7, 7 steps up, and we get that little turquoise dot that is on the Cartesian plane. We can go through and do the same for all the rest of our values of x we have here in this table. So for -3, we calculate the corresponding y value. We see we have that coordinate pair, and we go ahead and we plot it on the graph. For x is -2, we do the same thing. We get the corresponding y value, and we then plot at x is -2, y is -5. 2 to the left, 5 down, the pink point on that graph. X is -1, we do the same thing, and we have a coordinate pair which we can plot on the graph. When x is 0, we work out that the y value is -9, and we go ahead and we plot that on the graph. When x is 1, we calculate that. 1 squared minus 9 gives us -8, and we have a coordinate pair which we can go and plot on the graph. Carrying on in this way, we can plot all the points from our table on the graph. Now we can actually see that this set of points follows quite a nice sort of interesting looking curve. And we haven't plotted everything we could plot. I mean, we could go and work out what the y value is when x is 1/2, or what the y value is when x is 3 3/4, or what the y value is when x is 5. So we could carry on plotting a whole lot of points. And if we did, they should follow the pattern of what we're seeing here. So I'm going to draw in the pattern of what I am seeing. And that is a graph that looks like that. So this is what I'm thinking, that if I actually went and worked out all those little points in between, I'd end up having as a picture. Now, I can ask myself some questions about this. First thing to notice is just when I've drawn up this graph, do you see there up at the top right hand, I've actually labelled the graph, showing that this graph shows all the points that are related by that equation, y is equal to x squared minus 9. Now I can ask myself, are there points on this graph where the y value is 3? Well, y value is 3 steps up. So let's go and have a look. Is there any place on that graph where you're 3 steps up? Well, yes, absolutely, at that blue point over there. And we could, in fact, look in the other direction too, because that's also just 3 steps up. And we see that red dot is also a point where the y value in this graph is 3. We can then try and see, well, approximately what x value goes with it. Because remember, for each of these points on the graph, there's an x value together with a y value. Here the y value is 3. What is the x value? Well, if I come from that blue dot and just look at the x value that's going with it, it looks like it's about 3.5. We don't know it's exactly 3.5. It could be 3.6 or 3.4. We can't say for sure. And from the red, we can go down to the x-axis and see that the x value that goes along with that red point, where the y value is 3, is approximately negative 3.5. We can have a look at reading points from a graph. So here I have the graph of y equals 2x minus 1. I've already drawn it for you. I drew it up by taking some values for x, plunking them in that equation, working out the y, drawing up that sort of table of values, then plotting the points on the graph, joining them up. So I've drawn it for you already. Before we start reading points, I just want to go through a little vocab. We call this kind of graph a straight line graph for obvious reasons. And another way we can say straight line graph is to say linear graph. So you'll often hear that term used. And then this graph here is an increasing graph. And we call it increasing because as the x values go up, as they increase, so the y values also go up and increase. And really what you can see is basically it's increasing because as you move from left to right, the graph is going up. So it's an increasing graph. Okay, let's get to what we want to, which is reading points from the graph. If I ask, what is the y coordinate on the graph when x is 3? What I want to do then is look from where x is 3 and see where is that on the graph? Well, it's over there. Now all I need to do is read off the y value. And I can see that when x is 3, that pink point, its y value is 5. So reading from the graph, I get that the y value is 5. I can also get this by using the equation. You see, every single point that is on that line must fulfill this equation y is equal to 2x minus 1. That's how I drew up the graph, right? I substituted in the x value, got the y value, and then plotted the point. So every point on that graph must fulfill that equation. So I can easily work out the y value when x is 3 by simply substituting x is 3 into the equation, and I will work out that y is equal to 5. So 2 ways of doing it. All right, what if I want to know the x coordinate on the graph when y is negative 9? Well, again, I want to see where we are on the graph when you've got a y value of negative 9. So I go across and I see it's there. That point has a y value of negative 9. Now I want to know what that point's x value is, right? How far left is that point? Well, I can just look up and see, yes, that point is 4 units to the left. It's at negative 4. And so reading from the graph, I get x is negative 4. But again, I could use the equation because remember, every single point on the graph must obey the equation y is equal to 2x minus 1. Now in this case, I know the y value. So in place of y, I can put negative 9. And then I've got a simple equation to work out, right? Add 1 to both sides, I'll get negative 8 is 2x. And so then I'll get negative 4 is x, which I can write nicely as x equal to negative 4. Okay, let's look at some more. We need some vocab again first. When we talk about a y-intercept, we mean the point where the graph crosses or touches the y-axis. So the y-intercept is going to be the point where the graph crosses or touches the y-axis. And unsurprisingly, the x-intercept is going to be the point where the graph crosses or touches the x-axis. Let's look at an example here. What is the y-intercept of the graph? Well, the y-intercept, remember, is the point where the graph crosses the y-axis. So look at that y-axis and can you see where the graph is crossing the y-axis? Over there. And straight away we can read off from the graph that the y value is negative 1. What is the x value there? Well, you're on the y-axis. That means you haven't moved anywhere left or right. So your x value is 0. So the point where you cross, where the y-intercept is, where you cross the y-axis, is the point where the x value is 0 and the y value is -1 in this case. Now we can also do it by using the equation. The one thing we know for sure about a y-intercept is that it has to be sitting on the y-axis. And if it's sitting on the y-axis, we know we haven't moved left or right, and so the x value is 0. And because it's on the graph, it must fulfill the equation y is equal to 2x minus 1. And so we can substitute 0 into that equation, and we'll work it out. 2 times 0 is 0, subtract 1, and we get our answer of -1. And so we've got the same thing we got, obviously, from reading it off the graph, that the y-intercept has an x value of 0 and a y value of -1. It's that point, 0, -1. Okay, what about the x-intercept of a graph? Well, x-intercept again, where you cross the x-axis. So have a look at that x-axis, and can you see where the graph is cutting the x-axis? Well, you can see, hopefully quite easily, that it's cutting the x-axis at the point 1/2, 0. So that's where it is. And why is 0 for y? Well, obviously, you're on the x-axis, right? So you haven't gone anywhere up or down, so your y value is 0. And that's an important point, right? Your x-intercept will happen when your y value is 0, because if you're on the x-axis, your y value is 0. And this is going to help us if we want to try and work out the x-intercept by using the equation. We know that the x-intercept has to be on the x-axis, and on the x-axis you haven't moved up or down, and so the y value is 0. And so we also know the point is on the graph, so it must obey the equation y is equal to 2x minus 1. And so we can put 0 in place of y in that equation. And now we just have to solve that equation, and we will get that x is 1/2. We're going to have a look at one more graph story and use it to remind ourselves of some features of graphs. This is a graph that shows the height above a certain base level of tides in a lagoon over a 24-hour period. In other words, you've got this body of water, and the level of water either rises or drops depending on the time of the day. We need to decide what our independent variable and what our dependent variable are. Now, I've just said the height depends on the time of the day, and so obviously our independent variable is the time, and our dependent variable will be the height. Some things we might want to have a look at with this graph is, let's look at the first little while of the graph. Do you notice that in that first little while of the graph, as the time goes on, so the height is going up? And we talk about a graph like that as increasing. And in the real terms, what will that mean? It'll mean in that first period what is happening is the height of the water is rising all the time. So if you were asked, where is this graph increasing? You can see that it's between 0 and 12. We're looking at the times. Between 0 and 12, that the graph is increasing, that the tide is rising. Over here, you can see that as the time goes on, so the height is dropping, and there we call that decreasing. That's the decreasing portion of the graph. And if you were asked, where is this graph decreasing? Again, you could write it as an interval, saying between 12 and 24, the graph is decreasing. What does that mean in real terms? What we're talking about is from between time 12 and time 24, the tide is dropping in the lagoon. We might also be interested in this, the highest point that we can see on the graph. We call that highest point the maximum point, and in this case the maximum point has the time value of 12 and the height value of 5. And what does that mean? Well, we can say in words, at 12 hours the tide is at its highest level, and that is 5 meters above the base level. Obviously, we might well also be interested in the lowest point. And in fact, if you look down here, there are 2 places where we're at the lowest point. And the lowest point is called the minimum. And the coordinates of the minima in this case, 0, -5, and the other one, 24, -5. And we could put that into words. Let's talk about that second minimum. That would say, at 24 hours, the tide is at its lowest level, and that is 5 meters below the base level. One last thing we want to have a look at. This graph is called a continuous graph. And that is because there aren't any gaps in this graph. For every single point in time between 0 and 24, we have got information in this graph about what the height of that water level is. So there aren't any gaps. This is a continuous graph, and we can see it's a continuous graph because it's been drawn with a curve. The contrast would be something like this, which is a discrete graph. This is something we looked at earlier, the number of hours spent studying for a test versus the mark out of 100 for a test, and we had each individual learner plotted. This is a discrete graph made up of a whole lot of separate points. Okay, so that finishes our little look at the height of tides in a lagoon, but in particular a reminder of some of the types of features of graphs we might want to look at.